When Maxwell developed the classical theory of electromagnetism, he suggested that the speed of light was a limit. This was repeatedly proven by the Michelson-Morley experiment and many others. Einstein built upon this idea and developed special relativity. Special relativity made what was once considered absolute time dependent on speed, and space was now interpreted as 4 dimensions, 3 positions, and 1 time. After special relativity, all events in physics that approached the speed of light had to be solved using special relativity. Therefore, position vectors had to stretch with speed, and time had to contract. The mathematical expression of this was Lorentz's 4-dimensional special relativity matrix. As a result of this matrix, Minkowski space was formed. In our previous videos, we learned about the Lorentz transformation for 1 dimension and Minkowski spacetime. In this video, using this knowledge, we will hunt for the general Lorentz transformation matrix for 3 spatial dimensions. Good luck! As we have hunted, the Lorentz transformations in 1 dimension were found as those. If we write these equations in terms of the defined gamma and beta, we obtain their more organized forms. With those, this transformation is expressed as a 1-dimensional Lorentz matrix as follows. This matrix is for 1-dimensional special relativity. It has been proven by group theories that the laws of physics do not change under translation, rotation, and reflection of coordinates, meaning they are symmetric under such transformations. Let's consider we have a 3-dimensional spatial velocity. If we rotate our 1-dimensional coordinate system spatially so that we interpret this velocity in 1 dimension, can we still apply the laws of physics? Due to the rotational symmetry of physical laws, doing this doesn't change anything. We can use this advantage to find the general matrix of special relativity. The operations we will perform first involve finding rotation matrices. Then, using these matrices, rotate the coordinates so that a 3-dimensional velocity has only an x component. We apply the 1-dimensional Lorentz transformation matrix to this rotated system. Then, to ensure the result doesn't change, we must undo the coordinate rotation, so we multiply by the inverse of the rotation matrix. At the end of these operations, we will obtain the general Lorentz transformation. Let's begin. First, let's find the rotation matrices around the axes in 4-dimensional spacetime. Let the rotation angle around the x-axis be alpha, around the y-axis be beta, and around the z-axis be gamma. While spatial coordinates rotate at certain angles, the time axis does not rotate because time is the 4th dimension, and rotation occurs around the time axis. Rotation around the x-axis means the x-axis remains fixed, while the other axes y and z rotate. Let the coordinates of a point on the yz plane before rotation be y and z. When the axes rotate by an angle alpha, the new coordinates of this point on the new axis are given as y' and z'. Let's form triangles where y and z are the hypotenuses. We can find the unknown sides of these triangles trigonometrically. Be careful about whether the angles are positive or negative. Use the convention that angles pointing down in the coordinate system are negative and those pointing up are positive. You will soon realize that y' and z' can be written in terms of y and z by adding and subtracting the correct sides. Rearrange these equations. Let's write these values as the rotation matrix around the x-axis. Let's continue with rotation around y-axis. This time, the y-axis is fixed, and the other axes x and z rotate. Let the coordinates of a point on the xz plane before rotation be x and z. When the axes rotate by an angle beta, the new coordinates are x' and z'. Let's form triangles again and find the unknown sides trigonometrically. By adding and subtracting the correct sides, the values are found as. Let's write these values as the rotation matrix around the y-axis. Now let's do the same for rotation around the z-axis and obtain all the rotation matrices. Let's write these values as the rotation matrix. These matrices are used to rotate the coordinate system to desired angles. We want the velocity to have only an x component, so we need to find the angles alpha, beta, and gamma that satisfy this condition. Let's consider a velocity vector with components in x, y, and z directions, given as vx, vy, vz. First, let's arbitrarily rotate our coordinate system around the z-axis. The goal here is to zero out the y component of the velocity vector and move it entirely to the x-axis. The angle gamma that we must rotate is given by the geometry as, because the rotation matrix contains cosine and sine, we define them as. After this rotation, when we look from the z direction, we see that the velocity vector is now on our new x-axis. Next, let's rotate around the y-axis to zero out the z component. Now looking from the y direction, the velocity vector appears as a 2-dimensional vector in the xz plane, with components the square root of vx squared plus vy squared in the x direction and vz in the z direction. The magnitude of the vector remains the same, v. From the diagram, to bring the velocity onto the x-axis, we must rotate by a negative angle. So don't forget to include the negative angle in calculations. This rotation angle is found from the right triangle. The cosine and sine of this angle are these. After these rotations, the velocity vector is now on the new x-axis and is one-dimensional, so we don't need to rotate around the x-axis. Based on this, let's rewrite the rotation matrices. After applying the 1D Lorentz transformation, we must undo the rotation, so we take the inverses of the rotation matrices. Since all elements are real, the inverse is just the transpose of matrices. Now let's examine in which order we must multiply the matrices. We first rotated around the z-axis, so we write the RZ rotation matrix first. Then we rotated around the y-axis, so we multiply by RY. After the velocity vector becomes 1D along the x-axis, we apply the Lorentz transformation matrix. Then we undo the rotations in reverse order. First apply the inverse of the last rotation RY inverse, then the inverse of the first rotation RZ inverse. At the end of these steps, we obtain the general Lorentz transformation. If we perform these matrix multiplications step by step, we finally get this general Lorentz transformation matrix we have obtained fully defines how the spacetime coordinates change for a reference frame moving in any direction. Now, not only for the special cases moving in the x direction, but for any three-dimensional velocity vector v equals vx, vy, vz, we can show how the spatial and time components mix with each other. The first row of this matrix shows how the time component relates to all spatial components, while the remaining rows show how each spatial component interacts both with time and with other spatial components. Time mixes with space. Space mixes with time and with other spatial axes. This general form of the Lorentz transformation matrix mathematically represents the isotropic directionless and symmetric nature of relativity, which is one of the fundamental cornerstones of modern physics. This fundamental principle of special relativity states that the laws of nature must be the same in all inertial frames of reference. This requires that physical laws remain invariant under Lorentz transformations. These transformations ensure that while space-time coordinates are transformed into each other, physical quantities, like vectors and tensors, transform with appropriate mathematical rules. However, the truly important point is that the mathematical forms of the physical laws remain the same as a result of these transformations. For example, fundamental laws like Maxwell's equations or the conservation of energy momentum retain the same form no matter which inertial reference frame they are written in. This invariance guarantees that the fundamental structure of the universe is independent of the observer. Finally, along with these hunting, we can perform mathematical calculations for relativistic vectors using this matrix. So, with this, don't forget, everything comes from science.